Greetings and welcome to another installment of QuantSlob. This is 23 in our basic application series. This time around, we're going to motor on with part 4 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 3. If you want to enjoy all the action, and who wouldn't, I suggest you watch this mini-series in full. You can find it playlisted under the QuantSlob channel playlist tab. So let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Now, observing that this coin seems quite typical, and knowing nothing else about this coin, we fashion a decision theory style statistical test. We assume we are in possession of a fair coin, but we are prepared to challenge this belief if the result of 50 flips provides us with statistical evidence to the contrary. Now, we use the normal approximation, a standard normal distribution, to approximate, or if we prefer, to model the sampling distribution of our sample statistic proportion of heads. In this installment, we're going to look at a p-value version of a decision-style statistical hypothesis test, which is a little bit more popular, I think, nowadays. And there's actually really very little difference. The calculations are much the same, but there is a slight tweak in the methodology. In a p-value version of a decision-style statistical hypothesis test, we must still start by setting a level of significance. The probability of wrongly rejecting the null, otherwise thought of as the probability of making a so-called type 1 error. In our example earlier, we chose 0.02, 1 in 50. In a p-value decision test, we do not calculate a critical region as we do in a traditional decision theory style test. Rather, we immediately calculate our test statistic. And of essential importance here, the driving motivation behind making a decision between the null and alternative hypotheses is built around the basic idea that values that are far away from the center of the sampling distribution of our test statistic, our standard normal distribution, not only constitute evidence against the null hypothesis, but potentially offer evidence in favor of the alternative hypothesis. Our critical region or rejection region is a space that contains values that are rare if the null is true, and also contain values that may be common if in fact the alternative hypothesis is true. We set the probability of our critical region to be equal to our significance level in a way that is similar to the way in which we carved out our critical region earlier. To obtain our p-value, we're going to construct a region that contains values that are unlikely if the null is true, but potentially likely if the alternative is true. Sound familiar? A region with the smallest probability, that is the smallest area under our null sampling distribution here, but that includes our observed test statistic. In this case, from earlier, if you recall, about 1.41, the area probability of this region is our p-value. Another way to say this is, what would our quote-unquote significance level be if we required our quote-unquote rejection region to include our observation? And there are a number of resources that we can use to find this area here. We can use statistical software or a table or an online calculator, and I've included links to a number of resources in this video description for your enjoyment and exploration. Our result here, based on our observed test statistic, is 0.157 about. In other words, the combined area of the gold regions here is about 0.157. This is our p-value here. And our last step is to compare our p-value with the original significance level we specified. If our p-value is smaller than or equal to our significance level, we reject the null hypothesis. Otherwise, we fail to reject. And here, 0.157 is not smaller than 0.02, so we fail to reject, which of course is the exact same result we already obtained. Ultimately, when it comes to making a decision about our null hypothesis, either the decision theory style test we originally looked at or the p-value decision style approach will give us the same answer, certainly. Both of these flavors of statistical tests, that is the decision theory approach and the p-value decision style approach, are oriented towards informing a decision about the truthfulness of our alternative hypothesis, which in turn may promote a change in the status quo, a call to action here. This application occurs very often in industry, like a common example is clinical trials, where a pharmaceutical company has to decide whether or not to scale up production and promotion of a new medicine. Another example occurs in quality control, where a manufacturer has to decide whether or not their production equipment needs to be inspected or serviced or maybe even perhaps replaced. There is a third flavor of statistical test, which is extremely popular these days, simply because many scientific investigations don't really implicate that some decision has to be made. And this is simply a measure or degree of evidence type statistical test. And I'd love to be able to use the term evidence-based to describe this third flavor of statistical test, but the term evidence-based has sort of been co-opted by a number of different disciplines to mean something entirely different. In any case, a measure of evidence statistical test is very much the same as what we just looked at. However, we do not specify a level of significance at all. The resulting p-value is simply interpreted as a degree or amount of evidence. The smaller the p-value, the more the evidence against the null and in favor of the alternative hypothesis. Make sure to check out part 5, and that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more QuantSlob.